Hello, everybody. Welcome back. Today we're going to be looking at Unit 9.6, which is on something called coupled reactions, which may be a topic that you've never heard about or it's not typically taught in Chem 1, but let's get started. All right, so I'm sure you're very tired of hearing me say again and again what the different types of values for delta G indicate about a reaction, but let's just say something one more time. That if delta G comes out to be a positive number, that means the reaction is thermodynamically unfavorable. Okay, it's not going to happen spontaneously on its own. So does that mean that it can never be pushed? Well, no, there are things we can do to drive an unfavorable reaction, and that's what coupling is all about. So we can couple an unfavorable reaction with one that is favorable to make the overall process favorable. Now, you can't just pick any reaction you want to couple to this unfavorable one. You have to pick a reaction where they have a common intermediate. Let's review that term, guys, back from kinetics when we looked at reaction mechanisms. An intermediate was a product in one reaction and then was consumed as a reactant in a subsequent step. We're going to see coupled reaction problems very often in the context of Hess's law, which we have seen before. We saw it back in Unit 6. That's when we first learned it, and we revisited it a couple subunits back, but we're going to look at it again. So I want you to look at this example in front of you and focus on the two equations at the top. The first one is a decomposition of iron oxide, and look at its delta G value. It's very positive. That is a very unfavorable reaction in the forward direction. The second reaction, which has oxygen as a reactant, and oxygen is a product in the first reaction, so they have an intermediate in common, and that second reaction is favorable. And the question says, calculate delta G for this overall reaction. This is a Hess's law situation, guys. So let's just go through that thought process one more time on Hess's law. So we'll start here. Fe2O3, here it is. It's on the correct side. It has the correct coefficient. So this first reaction here, I don't have to flip it. I don't have to multiply it. It's good the way that it is. Okay, now 3 carbon monoxides. Well, here's carbon monoxide. It's on the correct side, but it has the wrong number. So we're going to need to multiply this whole equation times 3. So let's rewrite it. 3CO plus 3 halves O2 yields 3 carbon dioxides. And we're going to multiply that delta G value times 3 as well. And I get negative 850.5. Okay. And then I'm going to scribble through this equation because I don't want to get confused. I don't need it anymore. So now we're looking good. And if I add these two equations together, 3 halves O2 is going to cancel out. And if you look, everything that remains it matches up with this overall equation that I was supposed to get. I'm going to add my two values together. And here's the delta G of this overall reaction, negative 108.3. Running out of room, kilojoules. Okay, so when I put these two reactions together and have this different overall reaction, now the delta G of the overall is negative, it's favored. The point is, guys, let me clear the screen here. I took this first reaction here that is not favorable, and I coupled it to the one below, and when I put them together, the overall result was something favorable. So because these reactions share an intermediate, and when they are coupled together, it's going to yield an overall reaction with a negative delta G, okay, which is going to result in the overall process being favorable. So I want you guys to pause the video and try this one. It's the exact same sort of setup. You have two reactions. Think Hess's law. I want you to pause the video and answer both parts A and B. All right, so this was actually an even simpler one because I didn't have to flip either one of these equations around. I didn't even have to multiply them times anything. Okay, but again, the point is this first reaction is unfavored, so we couple it with the second reaction in the hopes that the overall reaction gives us a negative delta H. Let's just make sure. So the S cancels out. There's that common intermediate. And when I add my two reactions together, yep, I get this as my overall. And when I add my two delta G's together, I get that. And it is indeed negative. It is favored. And then the second question says, explain why the given reactions represented are suitable for coupling to produce a thermodynamically favored process. And guys, I essentially just said the exact same thing I had on the previous slide, that these reactions share an intermediate, and when they are coupled, have a delta G that is indeed negative. So that means the overall process is favored. So that was a quick one. Maybe something you've never learned before, but I hope you have learned a little something today, and I look forward to seeing you next time.